Hi. Now it is section 3.10 related rates. In this section, we look at questions that arise when multiple related quantities are changing with respect to a common variable such as time. Here the problem is to find the rate of change of one variable when others are given as data. Such a problem is called a related rates problem. Let's look at this example. Suppose we are pumping air into a spherical balloon. Then both the volume and radius of the balloon are increasing over time. So they are a variable. So here we are using V for volume and R for radius. Then they are related with this equation. V is 4/3 pi R cubed. Here V and R are functions of time. So we can differentiate them with respect to time. And by using chain rule, then we can obtain this equation. V t derivative is the same as V r derivative times r t derivative. And V r derivative is same as 4 pi r squared. So that equation is giving a relation between here the rates and dv over dt and dr over dt. So it is a related rates equation. Now here some others are given, then one can decide it. For example, here dv over dt and r are given, then we can decide dr over dt, right? Here we have a strategy for solving related rates problem. Okay, first of all, you have to name the variables and constants as functions of time. In this example, we named V and R as functions of time. And we can write an equation that relates the variables. That is now that equation. And here we can differentiate them with respect to time to obtain related rates equation, which is that one. And now the unknown can be found by using the known values. So that's the strategy. Okay. This example is a continuation of the previous example. A spherical balloon is inflated with helium at a rate of 100 pi cubed per minute. That means that V prime is 100 pi. How fast is balloon's radius increasing? So here, what we have to find is now the balloon's radius, the rate of change in balloon's radius, so that if it is r, then r prime, that's the unknown. At the instance, the radius is 5, which means that r equal 5. We already know from the previous example that v prime equal here 4 pi r squared times r prime. Okay, here the data, v prime is 100 pi, and now that is 4 pi, and r is 5, so the 5 is squared, and r prime. This part is 100 pi, so that we can reach at here r prime equals 1. Of course, that is foot per minute. Okay, so r prime is 1. We can find it. Okay, in this example, Now, what we have to do first is name the variable and write an equation, related equation, and differentiate the equation with respect to time. Okay. Here, the length of the rectangle, okay, is a rectangle problem, and it's increasing or decreasing at a rate of 2 centimeters per second, and its width is increasing at a rate of 2 centimeters per second. When the length is 12 and the width is 5, how fast is the area of rectangle changing? If we name here a variable and length, width, and area, then now at the last moment of the problem, it is asking here now what the A prime is. Okay, that's the unknown. We have to decide. But here, these three variables are related in this way. Area is same as L and W. So here now L and W are decreasing or increasing with respect to time. So they are function of time, and so that area A is also a function of time. So here we are making now time derivative, then that is same as here L prime W by using product rule, and plus L W prime. Okay, let's look at the problem again to find the data. Okay, we'll use a pencil in red. Okay, here length is decreasing along with that rate, which means that L prime equal -2. Now width is increasing. Okay, so that W prime is 2. When length is 12, so L is 12, and width is 5, means W is 5. Okay, by using this data, okay, L prime is -2, and width is 5, and plus L is 12 over there, there's 12, and W prime is 2. So that is 24 minus 10, so that the final answer must be 14. And of course, when you try to solve the problem, you can visualize by using your picture. For example, if you write down here that is L and W, then here A is related with L times W. Okay, here. Now sand falls from a conveyor belt at a rate of 10 cubic meters per minute. So this is a sort of volume onto a top of a conical pile. The height of the pile is always 3/8 of the base diameter. And how fast is the height of the pile increasing when the pile is 4 meters high? Okay, for this problem, and first start with a volume rate. So the volume and height and radius, they are variables. And we know that this is cone, so that volume is related with this equation, 1/3 pi r squared and times h. Here the condition here is that the height of the pile is always 3/8 of the base diameter, which means that height is 3/8 of diameter 2r. So that is the same as here 3/4r. Then now if you are using, okay, we rewrite this one in this way. H is, okay, 3/4r. If you try to use this here, plug over there, then right side of that one will be changed into a function of h, function of r. H is replaced by 3 over 4r, so that function of r. But here, the unknown is now from that line, the unknown is here h prime. So that is unknown. So that rather than this equation, from this one, we can get r equal here 4 over 3h. If we are using that equation and replace r with 4 over 3h here, then now the right side will become function of h. Okay. So v equal 1/3 then pi r squared h, which is same as 1/3 pi. R is now 4 over 3h squared and times h. So here that is, okay, in constants, there's 16 over 27 and pi, and here h cubed. Right? Now that is the relation, and from this one we try to get the related rates by differentiating the equation with respect to time. V prime equal now 16 over now 9, 3 will come out, and pi and h squared and h prime. Okay, so we need the values v prime and h values, but already we have here the theta. That means that this is a v prime is 10. Now the last moment here, when the pile is 4 meters high, that means h is now 4. So we are using this data. Then here that is 10 equal 16 over 9 pi, and h is 4 squared times h prime. Out of this one you can find h prime is something. That is a simple algebra. You can do it yourself. Okay, let's go to now this example. The White House, just 1 kilometer offshore. Okay, that is a picture made for you, and its beam of light rotates counterclockwise at a constant rate of 3 full circles per minute, so that the light beam is rotating in that direction. Now, at what rate is the image of a beam moving down the shoreline when the image is 1 kilometer from the spot on the shoreline? There is the warehouse. Okay, so for this problem, you have to name the variables. One is rotating, so which means now you may think the angle, so angle is theta. Now the problem is related with, now you have to find the rate of image moving down. So it is a sort of from here, the point, so that if you are considering the distance from that position down over there, then eventually what you have to find is the distance derivative. So that, let's say, the variable is x. So we have theta and x. The unknown is now x prime. That's the unknown you have to find. We named the variable, and we recognize what we have to do. Okay? Now, once you consider that is x, then already we know that is 1, and angle is now theta here, so that we can get the relation here now, tangent, okay, x is, okay, we start with now tangent of theta equal x over 1. Yeah, there's 1 and that is x. Okay, that is tangent theta. So that you can rewrite this one as here, x is tangent theta. Theta and x are functions of time, so that if we make a time derivative, then that is x prime equal now secant squared theta and theta prime. So the unknown is x prime, so we have to get theta and theta prime. Okay, let's look at the problem again. Here, its beam of light rotates counterclockwise at a constant rate. It's rotating at a constant rate of 3 full circles, which means that here theta prime equal full 3 circles, which means one circle is 2 pi, so that 3 times 2 pi must be 6 pi. Okay, we got that portion is 6 pi. Okay, so we have to find that one here. And now, we have to find some angle at the moment, but image is 1 kilometer, from the spot on here, the shoreline nearest the White House. That means that when x equal 1, so 1, 1, so that theta, out of that one, we can easily see theta is pi over 4, right? So we can get theta in this way. Now, secant is one of cosine. So cosine theta is now 1 over square root of 2. Square will make a 2, and reciprocal will make a 2 here now. In fact, cosine theta is 1 over square root of 2. It's square. Okay, let's write down here. Cosine pi over 4 will be here now 1 over square root of 2. Its square will make 1 over 2, and its reciprocal will make a 2. Okay, so we have here 2. So eventually we have now x prime is 12 pi. Okay? Of course, here now the unit must be kilometer per minute. Okay, we are using minute here. Okay, let's go to the last problem. A sliding ladder, a 13-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. Okay. Now, the first question is, how fast is the top of the ladder sliding down the wall then? Okay. Now, this is always now 13. As in this figure, you can use that position as x, that position as y. But now, rather than x and y, you can use here, that is base, and this is a height. Then, from Pythagorean theorem, we have always now here h squared plus b squared equal now 13 squared. So that once the data are given, then from this one, you can find that. Here the question is, how fast the top of the ladder sliding down means that we have to find h prime, right? That's the unknown we have to decide. Now, probably this will give enough data. Let's try here. A, we start with h squared plus b squared equal 13 squared. So from this one, now we make time derivative. So it's a 2h h prime plus 2b b prime equal 0. So that the unknown is h prime, so that h prime equal minus and b over h. Okay. And then, okay, b prime. So first we are moving this on the other side and divide by 2 and divide by h. Okay, so we recheck this one. Okay, here let's look at the problem statement. Okay, by the time, we don't know the time t. However, at the moment, the base is 12, which means b is 12. And then here, that is now, and a base is moving at the rate of 5 feet per second, which means now b prime is 5. Okay. So here we have b is 12, and so that now when b is 12, then we know that h must be 5. So that 5, 12, 13 are the Pythagorean triple. So we have all the required the quantities. That's minus b is 12 and h is 5 and b prime is now that is 5. Right? So that is minus 12. Okay, we got h prime minus 12. So here, and we can write down here h prime is minus 12. Okay, now for that one, here b prime equal 5 from the document. We can see that. Now second part. Okay, at what rate is the area of triangle formed by the letter wall and ground changing then? Okay, we want to find the rate of area, the rate of change in area, so that for that portion here we have h and b and area. They are variables, but these are related with this equation. Area is because it's triangle, half times b and h. Right? So the unknown is a prime. Of course, prime is time derivative. We can do it here now. A prime is half b prime. Okay, b prime h plus half b h prime. Okay, here half. What is b prime? Is 5. And h is now 5. Okay, that is 5. And plus half. Now b is 12. And here h prime is minus 12. Okay? So that that is the same as your half. Okay, that is 25 minus 144, and that is so half times, okay, minus 119. Okay, yeah, 119. So that there's minus of here 59.5. Okay. Yeah, we didn't make any mistake in computation. Okay. Now we'll go to the final part. At what rate is the angle theta between the letter and the ground changing then? Okay. Here now, and the theta is now new variable. Of course, here our early variables are h and B. And again, once theta is the angle between the letter and ground, now this is B and H. Then again, we can get here the equation, the relation between the variables. Tangent theta is H over B. So here now, unknown is what rate is the angle theta, so that theta prime is unknown for the final part. Okay, now C, there is a tangent theta equal H over B, and now if you are making derivative with respect to time, then here, that is here, secant squared theta times theta prime. Okay, right side, by using quotient rule, you can do it. Okay, that is B squared. And then, now, H prime times B minus here H B prime. Already here these quantities are already known from earlier and also from the document. We already know this quantity. Now we have to decide that one, then we can find the theta prime. Now at this moment anyway, that is now, okay, secant theta is the same as the reciprocal of the cosine theta. From this picture, already we know that cosine theta equal same as on the bottom is 13 and top is 12. Ratio between here, that one and hypotenuse. So that is cosine theta. So that for that one, we can get 13 over 12 and squared times theta prime is the same as, okay, B squared, that is 12 squared. And then on the top, here, H times B, okay, H prime times B, that is minus 12, and B is 12. And here, minus, what is H? H is 5. And then B prime is 5. Okay. So from this one, here now, we can multiply 12 squared both sides, then 13 squared theta prime equal minus of 12 squared plus 5 squared, which is the same as now 13 squared. 5, 12, 13, the Pythagorean triple, so that is minus 13 squared. Okay, so here we have theta prime equal minus 1. Okay, that's the final answer. Okay. Okay, that's the end of the section. Thank you.